Networking and Communication Systems Part 2. So in this set of slides we're going to continue talking about networking. We'll look at some more terminology. We'll review the OSI layers. We'll look at industrial buses, industrial Ethernet, and wireless protocols. So we've already kind of discussed this, but we want to just kind of reiterate it. The bit rate, how many bits can be transmitted per second? And then there's what we call a baud rate. Now a lot of times people kind of think of these as the same, but they're slightly different. The baud rate actually has to do with the number of transitions from going from a high to a low, from a 1 to a 0 or a 0 to a 1. For each second. And so the idea here is if you can encode multiple bits together without shifting from high to low, you can increase your baud rate. And then, of course, we've talked about the bandwidth. The bandwidth is the maximum rate of bits that can be transmitted across the medium channel, within a given time frame. Another aspect that we want to kind of discuss is power. So to power a device, if you have some kind of remote controller or even just a remote sensor, it's going to have some sort of power to collect the information and then actually to send the information. So there's a lot of different ways of doing this. One of them would just be that you have your data lines and then you have a separate power supply and separate power. However, if you're going a long distance, running extra cables and running extra power can really be a hindrance. And so there's a couple of different things. One of them is known as PoE, which is power over Ethernet. So the idea is over that Ethernet cable with those multiple, remember there were 4 pairs in an Ethernet cable. So if we could use those to send power to the device also, we can just run the one cable to both power and transmit the data on. And so power over Ethernet has gotten very popular. Now there is a limitation, they're small cables, so you can't get a lot of power, but you can get about 100 watts, which is actually quite a bit, and that'll go 100 meters. So if you remember, Ethernet was good for 100 meters for your data transmission. They also have kind of the opposite, or they, not the opposite, but we have just something called power over data line, which is kind of the same thing, but the difference is we have like just a single pair of wires, like a single pair Ethernet. So there's actually something called single pair Ethernet. So instead of having 4 pairs, you just have the 2 pairs, and you can actually, so you're sending the data on that same line. So that's kind of the difference between power over Ethernet. Actually uses one of the pairs that wasn't really getting used for data to send the power. But here we're sending the power on the same line as the data. And this for a single pair Ethernet is good for about 50 watts. Or if you run a second set, you can actually get up to 400 watts. We also have power source equipment. So this is just an acronym that people use a lot of times when they're referring to the power source for your remote devices or your IoT type devices. And just PD, which means a powered device. We have a PoE injector. So if you have a device that can use PoE, you need to have either a switch which will provide that, or you have to kind of have a injector which you put in line. The idea is that you can put it in line, but you put it like close to where the switch is to inject the power, and then you can run it out that 100 meters or however far that you need it to go within that 100-meter limit. Okay, timing is another issue. We've talked quite a bit already about timing, but there's a couple of new terms here that we want to just introduce. One of them is called determinism. So determinism is the guarantee that the message will arrive within that given time frame. So I've talked about that with being real time before, but this is just another term here, this idea of determinism, saying that we can pretty much bank on receiving the data within that given time frame. Another term is called jitter. So jitter has to do with the deviation of your clock cycle. So a clock is basically it ends up being usually like a square wave or whatever. It's a repeating waveform that is being sent to keep things in sync. And so if your clock cycle timing is varying, then that's referred to as jitter. We also have isochronous events, which means that we have like two or more events occurring simultaneously. Okay. There's another term, quality of service. So the quality of service is a measurement or a rating of the overall quality of the communication. And sometimes it's kind of used in a couple of different ways, but in general, you're right, we're just kind of like saying, okay, we know that we've received the data, and it's reliable data, or that we just actually have received it. Sometimes it's used as, you have like a quality of service says, okay, well, I'm transmitting this, and I assume that somebody's on the other end to receive it, but I don't necessarily am guaranteeing that they will receive it. So if they're like offline, then the question becomes, okay, well, do I retransmit it when they're back online, or do I just leave the data go? So these are just some different terms that we get into when we're dealing with communications. All right, so this is just a little graphic that I've came across online, but the interesting thing about this is it just kind of shows like the different layers, because we've already talked about like bus communications or peer-to-peer or machine-to-machine communications. And then, of course, we've talked about real-time Ethernet and then just standard Ethernet. And so this is just kind of giving a layer of kind of where those would reside within your overall system. So down here at the lower level, we have our sensors, our actuators, our remote I/O, and then one step up from that is where our controllers are at. So our PLC or variable frequency drives or whatever kind of controllers that we have. And so the communications, between those, it could be just like peer-to-peer, or maybe using one of the buses that we've kind of talked about, or maybe real-time Ethernet or Ethernet IP. But then as we get up to the higher level, we get into the HMI and the SCADA, and then from there up to like the office PCs or even the cloud, we can just use, doesn't have to be real time. So this is just a reminder of our OSI model. Okay, so remember we have these 7 layers in this model, And so down here we have the bottom two layers are like that physical layer, including the physical addressing. So we had the MAC address, or the physical address, which is at the Ethernet level. And then above that we have the network level. That's where the IP, or the logical addressing, goes. And then we had the ports. So up above that we have the transport layer, which is where the ports go, and the ports then give you direct access into the application layers. Also, just kind of want to remind you about these topologies, right? We had the point-to-point, we have a bus, we have the star topology, and the ring topology, and mesh topologies. Okay, so we're talking mainly today about actual industrial type of applications, okay, as opposed to, we talked before in the previous lecture, we focused mainly on just the internet, Ethernet, IPs, and things like that. So here we're just going to look at some of the different buses available and some of the other networking features. So we're going to start with RS-232. So RS-232 is a point-to-point type of connection where you have two devices and they transmit and receive. And so you can basically do this with like a 3-wire cable. You have a ground wire, or a common, and then you have a transmit. So the transmit from device 1 needs to go to the receive of device 2, and vice versa. And so usually they have like a special cable for this. It's kind of like the crossover cable we talked about for Ethernet, but this is for RS-232 communications. Now, this type of data is very simple, but it's not real fast, okay? So a lot of times it just runs at like 9600 baud, which is a very slow amount of, very little amount of data can be transmitted in a short amount of time for that. So it's not extremely fast, but it is very simple. And the range, just base range is good for 50 feet, but given certain conditions, you can actually get it to go 1,000 feet. So some pretty good range. The next step up is what they call the RS-485. RS-485 is very similar to the RS-232, but this is actually designed as a bus. And so here's just a little schematic kind of showing the wiring of this. So again, you have like a plus and a minus and a shielding wire. And there's a couple of resistors here that you have to allow all these different machines to communicate. And so you have multiple different machines all on the same, or devices all on the same network. So the distance can go up to maybe 500 feet for 24 gauge wire, which is very small. If you go for a little thicker wire, you can actually get it up to maybe about 800 feet. It's maybe just a little bit faster than the RS-232 connection. And it's good for about 32 devices. Okay, so not a whole bunch of devices, but quite a few. Then there's the CAN bus. We talked about the CAN bus is very popular on like automobiles, for one thing. CAN stands for Control Area Network. Okay. It's a very high integrity serial bus, and it has a higher speed. It's good for like 1 megabit per second, and you can put up to about 127 nodes on it. Okay, so that's quite a few compared to the other two that we talked about. Then we have Modbus. Okay, Modbus was actually created by Modicon in about 1979. Modicon was the company that first created the original PLC and kind of coined the term PC, programmable controller, which later became programmable logic controller. And now this is a bus, and so it can handle about 247 nodes plus the master. It's fairly easy to implement, okay, and it can actually use like an RS-232 or 485 wiring system. It's about 115K baud and good for about 2,000 feet. There's also Profibus. Profibus, I believe that was created by Siemens in Europe. And again, it's kind of built using the same physical layer as the RS-485. It can handle about 126 devices, but it has a much higher speed of about 12 million or megabits per second. So this is just kind of a little block diagram here showing the layers. So remember we have those 7 OSI layers, and what this is just kind of showing you is how this works. So it's basically, it uses the physical layers down here, and then it goes up to the application layer. So this particular bus really ignores the network, the transport, the session, and the presentation layers. So you basically have this application talks directly to the hardware, and it doesn't go through these other layers. So I guess maybe I wasn't clear on that before, but these, you don't necessarily have to go and use every single layer of this model. And so that's kind of what this is showing here, is that we're using the physical 485 bus, and then we have some addressing, which they call FDL, and then they're going right up to the application. So the application is coming directly to the hardware, where like if you're doing Ethernet, for instance, the difference is with Ethernet is you kind of have some other software pieces that are working like for your network. So you're right, with Ethernet, we had Node-RED using Ethernet, and we had Cloud9 using Ethernet. So both of them are using Ethernet, and they're using the transport layer, and they're using ports. They're using different ports, so that there's actually these pieces within the controller that are handling the IP addressing and use the port addressing and all these different layers, where what this is doing is this particular application is writing directly to this hardware, and that's why it can, instead of using a kind of middle piece of software in there. Okay, some other buses here I'll just kind of mention quickly. There's something called a CC Link. It was good for about 64 nodes, created in 1997. Okay, there's a GBIP, which stands for General Purpose Interface Bus. Okay, and this was created by National Instruments, and this is used quite a bit for instrument type things, for meters and things like that. So it allows you to like collect data from systems, so you can kind of monitor them, and you can actually control them with this also. All right, and then we've talked quite a bit in the previous lecture about Ethernet, and I talked about how Ethernet/IP, the original Ethernet, technically is not real time, and so there's several different modifications that were kind of built on Ethernet, but they modified down to like the hardware to, remember, technically Ethernet is that hardware layer, and so they've actually made some modifications to it to guarantee the real time in that. So we have something called Ethernet PowerLink, Ethernet CAT, C-A-T, Profinet, and then there's Modbus TCP, And then there's also Surcos. Now I mentioned Surcos before, but originally Surcos was using fiber optic, but they've adapted it to make use of Ethernet copper wires as opposed to fiber optics in there. Okay, so here's a slide that shows you up here at the top. We have Ethernet/IP. Okay, and this slide was from a Profinet link that I found. So up here you can kind of see what they're doing for Ethernet/IP is they're sending a clock signal to do that timing. Okay, but again, the catch here is that it's actually being done at the application layer is where they're doing their timing. And then there's the Surcos down here, and the Surcos is actually requires like some different physical hardware, and also like the EtherCAT that I mentioned. The difference here is that the clock signal is at the lower level down here, and it's so you actually can't use a standard switch for like something like EtherCAT. You can't just go out and buy an ordinary switch where you could with Ethernet/IP. So you actually have to have a switch that has been designed to handle this clock signal and this real-time guaranteed that the data is going to get through. All right. So here is the EtherCAT, okay, and showing you with these OSI layers here. And so again, down here at the physical layer and the data link, remember these are really very closely connected here. But the difference is that they've added extra parts down here at the data link to guarantee that real time. And the other thing that they do is they just bypass layers 3 and 4. So because they're just doing local addressing. So the big thing about like TCP/IP on the layers 3 and 4 here is these allow us to send the data across multiple different physical networks, where EtherCAT is really designed to just transport the data on the local network and not have it route. Now you can do some routing with it, but it's not really designed to be like routing out to the internet and things like that. Okay, so here's Profinet. Again, Profinet's kind of doing the same thing. It actually has two parts. It has one part that can use the IP and the TCP/IP layers, but for the real-time piece of it, they skip those layers. And so the Profinet application has like a real-time portion that skips those and goes directly down to the physical Ethernet layer. But again, this Ethernet layer has been modified to guarantee that clock signal. All right, so this is just the Ethernet IP model, which I guess I've kind of talked plenty about here. So again, the idea here is the real time is done up at the higher layer, at the application layer, and so the reason this works is just because Ethernet is so fast that there's seldom very delays, especially when you're just doing it on a local network. If you're actually then trying to forward this out to the cloud, you're definitely going to lose any sort of real-time guarantees because your hardware isn't supporting it. It's being done more at the application layer. Okay, so with Modbus, I mentioned Modbus earlier. Modbus is originally started as a bus, and it was using like the 485 type of hardware. But what they did was they sort of adapted that and evolved that so that it can actually use Ethernet. But again, it's has some modified hardware, or excuse me, actually this uses standard, this uses standard hardware and switches. And so again, it's doing like Ethernet slash IP to handle the real time piece, like Ethernet slash IP. All right. And then there's the Circos. As I mentioned before, originally Circos was fiber optic, but it's been adapted or evolved so that it can actually use Ethernet style equipment. All right, so here's a little chart that I found. Now, this one's gotten a little bit older. This one was from 2018, and this I need to see if I can find a newer one here, but this one here just shows like a little pie chart showing you the how much each of these different Ethernet type protocols are being used. And so you can see like Ethernet slash IP at this time was about 27%. So, and then Profinet was about 29%. And then just standard Ethernet was another 17%. So if you just take those three, you can see that that was, 70 some percent of the overall communications is done by either Ethernet slash industrial protocol, or Profinet. And like I say, I don't really have a newer chart on this, but I believe that it's even more of that. So these other ones over here don't really have a lot of market share. So, you might be using those, but most of the newer ones I've seen going in are either Ethernet slash industrial protocol or Profinet. All right, so here's just a little chart that gives you an idea about the data rate and the jitter and the response time. So you can see here again, these are all based on the Ethernet hardware. So these are either Ethernet IP, that PowerLink, Profinet, or Circos, or EtherCAT. And so if you look at these and look at the speed, this is where things come in. So with Ethernet IP and the PowerLink, the response time for 100 axles. So they're saying we're going to control 100 servo motors using Ethernet IP. That's what this chart was. They tested this and they came up and said this gave us reliable access at a speed of 1 millisecond for 100 axles, and very little jitter, and a data rate of 100 megabits per second, which they all have the same data rate. Okay, so the amount of data that you can transfer is there. But what they're saying here is the response time, how they were able to get a response to all 100 axles, and it took 1 millisecond for Ethernet slash IP, a little less than that for the Ethernet PowerLink protocol. Remember, these are all just different protocols that you can choose. And the big thing here is you see like EtherCAT especially was a tenth of a millisecond. Okay, so it's basically 10 times faster than these other ones. Again, the idea is with EtherCAT is you had to have physical hardware, the switches, the low-level hardware. You had to buy different hardware. You couldn't just use standard off-the-shelf like Ethernet slash IP is using. But you get 10 times faster response. And so that's kind of the thing. It's like, well, why would I use that? Why would it? Because I'm going to have to buy special hardware, which is, of course, is going to be more expensive. But it gives you a response time 10 times as fast as these other ones. All right, so this chart here, again, it's showing these OSI layers, and just kind of trying to show you the communications here. And again, the difference is the top chart here is the standard Ethernet / IP. So this is using standard. See right down here at layers 1 and 2 is just a standard Ethernet device. So the Modbus, the standard Profinet, okay, not the real-time Profinet, but like a standard Profinet, and Ethernet Industrial Protocol is sitting here, and it's using standard Ethernet controller hardware, which means the cost is lower, but again, you're not quite guaranteed that real time. Where these ones down here, we have the Circos, the EtherCAT, and then the Profi real time. Down here, they had to recreate the switches. They had to modify the standard switches, and they built special switches that handle the clock signal down here at the physical layer to guarantee real-time delivery. All right, so let's just review the wireless. We talked a little bit about this before. We have, of course, Wi-Fi, and then we have Bluetooth and Bluetooth low energy, and then, of course, there's just standard radio frequency or cellular, and then there was that LoRa, long range protocol, and also LPWAN, which is a low power wide area network, similar in a lot of ways to the LoRa. So when we look at this, I think I gave you this chart before here. You know, up here at Wi-Fi, we have very high frequency. Not a lot of range, right? Only good for maybe 300 feet for Wi-Fi, but very, very fast in a large number of devices. And then we have Bluetooth low energy. So BLE, Bluetooth low energy version 5. Okay, it's using the same frequency as Wi-Fi, not quite as fast. Okay, has a little bit better battery life, but can only handle about 32,000 devices. And then there's that LoRa, which stands for long range. Okay, and this was unlicensed, and so it uses in the United States, it uses the frequency 915 megahertz is the frequency that it uses, and it's good for long range. So see how this is good for about possibly 20 kilometers without any air interference, and it uses very little battery life. I mean, this chart, they said 10 plus years. I mean, I don't know how big of a battery that was. And then they give a roundabout number of, you can put about 50,000 devices on the same node. And then, of course, there's cellular. Now, cellular uses licensed frequencies, and so you have to pay for a cellular service. And so it gets kind of expensive. It tends to be pretty hard on batteries, but you can have a large number of devices, and it's good for, say 10 miles for 4G, maybe a little less than that for 5G. But and then there's this thing I mentioned before was MyThings, which is also, I believe it's unlicensed. It's in that 900 megahertz, and it's good for about 20 miles, and very low battery, very low power, so long battery life, and supposedly it's a good for like 1 million devices. All right, so this chart again is just kind of showing a lot of these different things, Wi-Fi, wireless charts and things here. You just kind of look at this, if you're trying to decide, what to use, you can kind of use this chart to decide whether it's good for these types of applications here. And this chart, I did show you this chart before. Again, it's kind of color coded for the cost. So the darker it is, the more it costs. On the right or on the bottom, we have the range. So you have the long distance, like the MyThings and the LoRa technologies, and then the vertical is the speed. So the higher up you are, the faster, the more data can be transferred. Okay, and this is just that same chart again I showed you before on the previous lecture, just showing you the different number of devices and battery range and stuff. So I just put it in these slides again. Okay, so if we look at LoRa, okay, again, there's this ESP32 device that we're going to use this for one of the upcoming labs here, and just to kind of see how this works and to use this technology. The other technology I wanted to kind of talk about was Bluetooth Low Energy. Okay, so Bluetooth Low Energy is very popular for, relatively close things. And the way this works, it actually uses 40 different radio frequency channels. 3 of them are used for advertising. Now, what they mean by advertising is the fact that your devices, when when you're carrying around your cell phone, like when you walk into like a restaurant or something, it'll kind of like check and see whether it can connect to their local Wi-Fi. So it has to like send out a message and say, hey, look, I'm here, can you give me an IP? Well, Bluetooth kind of does that same thing. So what it does is it's advertising. It's saying, hey, I'm here, I'm within range, I'm powered on, do you have any data you want to send to me, or maybe I want to send you some data, or will you take it? That kind of stuff is what they're referring to. So you're just kind of alerting yourself that I'm here. But the idea of this is that it'll hop between these 40 different frequencies in case there's a lot of devices on there. So, if you have lots and lots of devices that are all trying to communicate at the same time, it'll say, well, this particular frequency is kind of busy. Let me go up to the next one and see if maybe I can communicate on that one a little bit better. All right, so this Bluetooth Low Energy is kind of set up with like a central piece and then a peripheral. So you have like one of the devices is like a master or main device, and so it handles the timing. And then it scans for other devices to see whether they're in range and turned on. So, sometimes a lot of these remote devices, maybe they're not on all the time. They may only come on for a little while and then they go back off. So it needs to scan, not constantly maybe, but, multiple times in a minute anyhow, probably, to see if there's any devices that just came into range or came back online, kind of thing. Okay, and then you have these peripherals which will send out that advertising packet that I was just talking about to the central and say, hey, I'm here, I'm turned on, and I'm within range, and let's communicate. Okay, so the way the Bluetooth Low Energy is set up is they kind of have this layered, the data is layered, so it's kind of like encapsulation, kind of what we talked about with Ethernet. So you have what they call a profile. Within a profile you have a service. That service can have multiple characteristics, and then a characteristic will have various different things, like it'll have a property, it'll have a value, and a descriptor. Now, one of the most common you would see would be something like a battery service. So you have a Bluetooth device, right? If it's running off a battery, which many of them, most of them probably do. So there's a designated battery service. So it has an ID number here specifically for this. Now, UUID stands for Universally Unique ID. And so it's theoretically unique, but in reality, it can be duplicated. But this one here is reserved for the battery service. So you have this battery service, and you have an ID for that, and then you have the battery level. So the characteristic is like the battery level, and so within the battery level, you can have a descriptor, and then the value, whether you're at 5% or 50% or 100%, whatever your battery level is. All right. Another thing when we're talking about Wi-Fi that we talk about a lot is the signal strength. Okay, so we have another acronym here, RSSI, which stands for Received Signal Strength Indicator. So these devices will send out a message, and it'll include a piece so that they can kind of determine the signal strength. Okay, and so a relative index of a scale from varies, so it's a little confusing sometimes because you might think, the scale's from 0 to 100. So if I'm getting 100, that's really, really good. That's about the best I can do. However, sometimes they use different scales, like they might use a scale from 0 to 255. So if you're getting a strength of 100, but the scale actually goes to 255, that's way below 50%. So but in general, the higher the value, the stronger the signal. Another sort of measurement of that is what they call the decibel. So the decibel is an absolute measurement of strength. So you can, if you have this ability, you can actually measure how much power is in the signal. And I see I misspelled measurement there, but it tells you how much power is in it. So you can, like say, if you have that ability, you can actually measure that and figure out how many watts or milliwatts it'll be. So dB lowercase m stands for milliwatt, or not milliwatt, but millidecibels. So it's very low power. All right, so here's a little chart just showing you kind of a signal strength sort of thing. So if you're getting a strength of minus 30 dBms, millidecibels, that is actually a very strong signal. Okay, and if you're down at like minus 90, it's like, well, I can sort of hear it, but it's not reliable at all. Okay, so LoRa, we already kind of talked about this, right? It uses unlicensed frequencies. If you have proper antennas and you don't have, obstacles in the way, you can get up to maybe 20 or 30 miles with it. It's very low power, okay? And it can work as a mesh system if you want it to. And there's just standard LoRa, long range, and then there's LoRa WAN, and so this is kind of like a more complex configuration here. But if you have this set up, supposedly it's good for like 1 billion devices all communicating together. So some of the most common things that we see for IoT are the one wire that we've discussed, Bluetooth or Bluetooth Low Energy, Wi-Fi, cellular, Ethernet, the CAN, and the LoRa. The one wire protocol, okay, uses technically it uses two wires because you still need a ground wire, but the idea here is with a single wire you can have power and data. And so what we're going to do for the upcoming lab is we're going to use a one wire temperature sensor to read temperature, and then we're going to send it out through the wireless, the LoRa, and we're going to transmit it to another device, and and we're going to send our temperature out to like other people in the classroom, and then they're going to send us their temperature. Okay, we also have the other one, which is I2C, which is integrated circuit to integrated circuit communications. This here just uses two wires. Okay, you have one wire is a clock signal, and then the other one is a data signal, and then again there is a ground wire you need for that. And then there's SPI, which is a 4-wire setup, and then the CAN, the controller area network, in there. So here's the wiring diagram for a one-wire communications. Okay, so the what you have here is you have your controller, and then you have a 4.7K resistor, which they have what they call a pull-up. So you pull this up to VCC. Now VCC just means like your supply voltage. Okay, it actually, the V stands for voltage and the CC stands for common collector. Sometimes you'll see something like VDD, which stands for voltage drain, meaning common drain, depending on the type of transistors that you're using. But the idea here is you have your master, and it's going to be like a controller or something, so it's going to have power supplied. So it's basically then going to, if you're using the one wire to send power to the other devices, you have what they call like the slave devices, like a temperature sensor or something. And so you can power these with their own voltage source if it's available. But if you want to use the one wire, then what you would do is you would take the voltage, positive voltage signal, and actually tie that to ground, and then you just wire up the data. Now, one thing I will say, I've noticed when you buy some of these like temperature sensors and things that are using one wire, some of them do not support the actual one wire. They actually still need their own separate power to them. So technically they're not supposed to. They're supposed to be able to be wired as I show in the slide here, but if it doesn't work, try providing it its own voltage source on the plus pin. This is the plus pin VDD here. All right, so that's it for this lecture.